Hi everyone, I'm Chris and welcome back to the lecture on linear regression of this machine learning course. This section is about model selection. Before a machine learning model can be applied to data, the data itself needs to be preprocessed. For example, we need to take care of missing values or normalize the data. Then, we can specify a model type. This can be, for example, a linear model or a neural network. After that, we can choose a cost function. This function evaluates the quality of a model with respect to a given dataset. With this cost function, the model is fitted to data. This is called model training. Now, we could choose different model types to specify our model. The question now is, how do we know which model is the best one? And not only on the training data, but also in the real-world application. We will evaluate how to select the best model. First, we consider a generalization of the linear model. We start with a multiple linear regression model with capital K variables x1, x2 up to x capital K. The model is beta 0 plus beta 1 times x1 plus and so on plus beta capital K times x capital K. We transform the variable xk to x to the power of k. This gives a polynomial regression model with a polynomial degree capital K. Capital K is a so-called hyperparameter of this model. In contrast to the trainable parameters beta, the hyperparameter is not determined by fitting the model to the data. The hyperparameter capital K needs to be determined in advance. Otherwise, you would not know how many trainable parameters beta you have. So first, select the model type. Then, specify the hyperparameters. Second, determine the trainable parameters by fitting the model to data. But how to select the hyperparameter capital K for the polynomial degree? Here we have three different models with a different polynomial degree. On the left side, the degree is 1, which gives a linear model. The model does not fit the data very well. The data has a more complex structure than the model. This is called underfitting. On the right side, the polynomial degree is 100. The curve fits perfectly all data points. But it seems that it fits also statistical variations. This effect is called overfitting. The model shown in the middle seems just right. But how can we verify this? This can be done with cross-validation. The idea is to split the training dataset. The model is trained on one part of the data. And on the other part, the accuracy of the model predictions is checked. The cost function value for these data points gives the accuracy of the model prediction for these validation data points. Let's reconsider our polynomial regression model with a degree 100. So, we skip the light blue data points from our training data and fit our model just to the dark blue data points. The resulting green curve will still fit the trained dark blue dots perfectly. but not the light blue ones anymore. We can use these left out data points to calculate the mean absolute error just for these light blue data points. Then we can compare the results to a different model. For example, the orange model shown here. It has smaller deviations to this validation data to the light blue dots. So here we would prefer the orange model over the green one. This idea can be implemented more accurately. This leads to the Kfault cross-validation. The model is trained on the k-1 over kth part of the data. Then the model quality is estimated on the left out part of the data. This left out part is called the validation data. This procedure can be performed k times by shuffling the data selection for training and validation. Note that the k resulting validation data sets are called folds. On the right side, the 5-fold cross-validation is illustrated. So the results are 5 scores for the 5 different validations. Then you just select the model with the best scores. It is often beneficial to consider not only the mean value of the validation scores, but also the variance or the maximal score. If two models have a similar mean score, you usually should prefer the one with less variance in the scores. This indicates a much more stable and robust model. In practice, cross-validation can be a bit tricky. In order to get valid scores, you need to ensure that the selection of the training and validation folds are representative. A bad example is illustrated on the upper right. All blue data points are in the training set, and the green stars are in the validation set. Of course, the model has no chance to learn something about the range of the green stars. To ensure that the folds are representative, they should follow a similar distribution function. Often, the data is selected at random into the folds. Typically, this is a good approach. But not for time series data. Take a look on the example on the lower right. The data for validation and training are picked at random. The data points itself are very close to each other. This is why both training and validation sets contain very similar data points. A model with high accuracy on the training data has always a high accuracy on the validation data. So, selecting data points into the folds at random is not so good for time series data. You should consider the correlation length. Divide your time series into parts with respect to the correlation length, and then put the parts into different folds. Section finished. If you liked this video, please click the like button and consider to subscribe this channel. If you have any comments or questions, please leave a comment down below. And thanks again for listening. See you in the next section.